Hello all, good morning. Welcome to Unacademy. Today we will going to see our next lecture on discrete mathematics. In this lecture we will cover recurrence relation, which is most important topic of discrete mathematics. Recurrence relation that we will see in both the types of recurrence relation, homogeneous linear recurrence relation of second order, as well as a non-homogeneous recurrence relation by using generating function and by using the different conditions, okay, that we will see in this lecture. But before going to start this, let me introduce myself. Myself, Dhanashree. I completed my MSc in Mathematics from Mumbai University and also having 13 plus years of teaching experience, and I mentored more than 10,000 plus students for the engineering. Okay. Here I am going to tell you how to install the Unacademy's Learning app. First, go to your mobile's Play Store app, then search Unacademy's Learning app. Here you can see the arrow is blinking here. So search Unacademy's Learning app. After that, install the Unacademy's Learning app. And then here you manage your goal. Here जैसे कि हम लोग यहाँ पे अभी GATE and ESE के लिए पढ़ रहे हैं, so you can manage your goal here. So here GATE and ESE, and then you can take any subscription plan here, either for plus subscription, free courses, special classes. It is up to you. So which course, which plan you want to take and which course you want to take, that you can select here, and then get subscription. Press the get subscription button, and then after that a subscription plan for GATE and ESE. So you can select here either for 12 months plan or for 24 months plan. If you are going to preparing for the GATE 2023, then I will suggest you can go for the 24 months plan, so that it will cover most of the things and which is very helpful for to crack your GATE 2023. You will go for the 24 months plan, and here you can use my promo code, that is DSP, to get the 10% discount on your subscription fees. Okay, so it's the most important benefit for you if you use my promo code DSP, so that you will get a 10% discount on your subscription fees. Now next is here step 7. Here you can choose payment method either by debit card, credit card, EMI, UPI, wallet pay, and net banking. It is up to you. You can take any subscription. So here any payment method, so that you, it is easy to pay your subscription fees. Next, to unlock the free plan of Unacademy, you can use my promo code, that is DSP, for the special classes, for the live test series, and for quiz and Unacademy Combat. Now let's start our actual topic, that is recurrence relation. Okay. In this recurrence relation, we will see a recurrence relation for the sequence A0, A1, A2 and so on is an equation that relates n to certain of its preceders A0, A1, A2 up to n minus 1. A difference equation is a specific type of recurrence relation. Now see, when we know the first two steps, then we can generate a recurrence relation with the preceders A0, A1, A2 up to n minus 1. With the help of this, we can find out an. Okay, so we can generate a difference equation or recurrence relation with the given preceders. Okay. Now, the most well-known example here is Fibonacci sequence. Okay, that is most important example is Fibonacci sequence or Fibonacci numbers. The Fibonacci numbers are defined using the relation Fn is equal to Fn minus 1 plus Fn minus 2 with the initial conditions F0 is equal to 0 and F1 is equal to 1. Okay, यहाँ पे एक बहुत अच्छी story है how to generate the Fibonacci sequence. Okay, so keep the story apart, and here you can see the first initial condition. The pair of rabbits are kept in an enclosure for a certain periods, and the pair of rabbits gets matured and for take a maturation period for 1 month, and after that it will give a birth of new pair of rabbits. Okay, so that process while giving the maturation period is 1 month, and after maturation it will gives a one more pair of rabbits, birth to the one more pair of rabbits. So that is initial condition. So initially the pair of rabbits kept in an enclosure, it will take a, so initially as it is, so if f1 is equal to 1, then we can find out the f2 here. F2 is equal to, you will get the initial pair of rabbits that will take a maturation period. So you will get for 1 month, so one pair as it is here, f2 is equal to as it is. Now f3 will be here. So F3 will be here. This original one pair of rabbits takes 1 month maturation period, and its already matured pair gives birth rise to the new pair of rabbits. That will it will becomes F3 is equal to 3, right? Here 1 plus 2. Original pair plus one more pair of newly born pair, that is 1 plus 1 is equal to here 2. So you will get here two pair of rabbits. So if you see here in the next month, the original pair again will take a maturation period. The newly born pair will take a maturation period for 1 month, and the new pair of rabbits, the original pair of rabbits again gives you one more pair of rabbits. So here we'll get the original pair plus newly born plus this original one more gives you one more pair of rabbits. Now if you observe, now similarly F5 you will get here. F5 it means the original pair plus newly born pair plus newly born pair already takes maturation period. It will give birth to the new pair of rabbits, and plus here newly born pair already it will take a maturation period, and the original pair also gives you one more pair of rabbits. So F5 will be 5. Now if you observe here, F0 is equal to, the next term will be F1 will be F0 plus 1, right? So if 1 plus original pair here 1, so 0 plus 1 is 1, so F1 is equal to 1, F2 is equal to 0 plus 1, that is 1. Now F3 is equal to 1 plus 1, that is 2. F4 is equal to 2 plus 1, that is 3. F5 is equal to 3 plus 2, that is 5. So the next term will be gives you the preceding two pairs, addition of preceding two pairs. So in this way the Fibonacci sequence generates. Okay, so this is well-known Fibonacci sequence. Here Fn is equal to Fn minus 1 plus Fn minus 2. This is well-known Fibonacci sequence. This is well-known recurrence relation called as Fibonacci sequence, with initial conditions f0 is equal to 0 and f1 is equal to 1. Now we go further. So next is homogeneous recurrence relation. So what you first of all we will see the general form of a recurrence relation. As we have seen this example, Fn is equal to Fn minus 1 plus Fn minus 2. In this the original sequence is Fn is equal to Fn minus 1 plus Fn minus 2. Now this is the form of a recurrence relation. Now we will see the general form of the recurrence relation. A kth order linear recurrence relation for the sequence x0, x1, x2 and so on has the form xn is equal to a1 xn minus 1 plus a2 xn minus 2 plus and so on plus ak xn minus k plus Fn for n greater than or equal to k, where a1, a2 up to ak are constants and fk, fk plus 1 and so on is some given sequence. We shall restrict our attention to the homogeneous linear recurrence relation, those which all the Fn are 0. These are the recurrence relations of the form xn is equal to a1 xn minus 1 plus a2 xn minus 2 plus and so on plus ak xn minus k for n greater than or equal to k or equivalently. Now we'll see here. We'll see the generating function here. For example, consider the recurrence relation. For example, consider the recurrence relation. Consider the recurrence relation. Okay. here xn plus 2xn minus 1 minus 15xn minus 2 is equal to 0 for n is greater than or equal to 2, where x0 is equal to 0 and x1 is equal to 1. Okay, x0 is equal to 0 and x1 is equal to 1. Now here generating function we can write g of z is equal to the original form x1 plus x1z plus x2z square plus and so on plus x3z cube and plus and so on. With the generating function of the sequence, with the generating function of the sequence x1, x2, x0, x1, x2 and so on. Okay? Now, after multiplying by z and z square, we will multiply this equation by z and z square to get this equation in the form of generating function. Okay, so multiplying g of z by z and multiplying g of z by z square. So you will get z into g of z is equal to here x0z plus x1z square plus x2z cube plus and so on. Okay, exactly similar way you will get z after multiplying by z square to g of z. You will get g of z x0 z square plus x1 z cube plus and so on x2 z raised to 4 plus and so on. Okay. We form the expression here. We form the expression here g of z plus 2 into z g of z minus 15z square into g of z. Because of the recurrence relation, because of the recurrence relation, most of the terms are cancelled. Okay, most of the terms are cancelled, right? And so we get here g of z into bracket 1 plus 2z minus 15z square is equal to x0 plus x1 plus 2x0 into z, right? Now take the g of z here common, so you will get g of z into bracket 1 plus 2z minus 15z square is equal to x0 plus x1 x0. Now if you add this and subtract like this, so you will get these terms only. So using the initial values, that we know that the consider the recurrence relation, initial value x0 is equal to 0 and x1 is equal to 1. Okay, using the initial values, we get x0 is equal to 0 and x1 is equal to 1, and dividing by 1 plus 2z minus 15z square leads to the closed form, here g of z is equal to, we'll get g of z is equal to z upon 1 plus 2z minus 15z square. Okay, now here we have 1 plus 2z minus 15z square is equal to 1 minus 3z into 1 plus 5z, right? And we want to find the numbers. We want to find the numbers a and b such that here z upon, by using partial fractions, we'll get 1 upon 2z minus 15z square is equal to a upon 1 minus 3z plus b upon 1 plus 5z, right? So after finding out solving these equations, we'll get A is equal to 1 by 8 and B is equal to minus 1 by 8. Okay, thus we'll get G of Z is equal to, using generating function we are solving here. So 1 by 8 is common. So 1 upon 1 minus 3Z minus 1 by 8 into 1 upon 1 plus 5Z. Right? So using the formula for 1 minus Z bracket raised to minus 1, replacing Z by 3Z for the first term and Z by minus 5Z for the second term, we obtain here G of Z is equal to 1 by 8 into bracket 1 plus 3Z plus 3 square Z square plus 3 cube Z cube plus and so on is equal to minus 1 by 8 into bracket 1 minus 5Z plus 5 square Z square minus 5 cube Z cube plus and so on. The coefficient of Z raised to n, here we can see the coefficient of Z raised to n in G of Z is xn, and from the expression we get here xn is equal to 1 by 8 into 3 raised to n minus 1 by 8 into minus 5 raised to n. Okay, so this is your expression. So this is your recurrence relation. Xn is equal to this. Okay, I hope you are getting it clear. We find out the recurrence relation by using generating function. Now yesterday's lecture we have seen what you mean by generating function, right? So generating function we have already seen in the last lecture, and with the help of that generating function we find out the recurrence relation. Okay? Now solve the following recurrence relation here. Solve the following recurrence relation AR minus. Now see, as we have seen here, if the this is homogeneous recurrence relation, it means here Fn is equal to 0. Okay, here Fn are 0. We'll see. Here Fn is 0 here. Fn are 0 for this expression. Okay, now for the homogeneous recurrence relation, so here Fn is equal to 0, so we will write down the given recurrence relation in the form of characteristic equation. First we will find out the characteristic equation and then solve this depending upon the nature of roots. If the roots are real and distinct and repeated, then we will write down the solution accordingly. Okay, now we will see this example in which the first of all we will convert the given recurrence relation into characteristic equation. Okay, so the given solve the recurrence relation. Here recurrence relation AR is AR minus 7 AR minus 1 plus 10 AR minus 2 is equal to 0, given that A0 is equal to 0 and A1 is equal to 1. Okay, so the characteristic equation of this recurrence relation is the characteristic equation of the recurrence relation. The characteristic equation of the recurrence relation is here. Now see how to write down. This is your constant AR minus 2. This is your constant. This is your value of lambda AR minus 1, and this is your value of lambda square, right? So there is no any coefficient for the lambda square. So we will write down here lambda square minus 7 lambda plus 10 is equal to 0. Okay, now this is your characteristic equation for the given recurrence relation. Now we'll find out the roots of this characteristic equation. So you will get lambda square minus 5 lambda minus 2 lambda plus 10 is equal to 0. So lambda into bracket lambda minus 5 minus 2 into bracket lambda minus 5 is equal to 0. So you will get lambda minus 5 into lambda minus 2 is equal to 0. So if you observe here, lambda minus 5 is equal to 0, lambda minus 2 is equal to 0. So which implies lambda is equal to 5 and lambda is equal to 2. Now if you observe, the roots of this given equation, given characteristic equations are distinct, right? The roots are distinct. Therefore, solution of the given recurrence relation is here, and right here, roots of the characteristic equation roots of the characteristic equations are real and distinct. The roots of the characteristic equations are real and distinct. Then roots of the characteristic equation are real and distinct. Then we have solution for this. Solution here, AR is equal to, because your equation in the form of AR. So here AR is equal to A into 5 raised to R plus B into 2 raised to R. A into 5 raised to R plus B into 2 raised to R, where A and B are constant. Where A and B are constant. Right? To find A and B, we will put R is equal to 0. Okay, we will use the initial conditions because A0 and A1 are given. Right? Here A0 is equal to 0 and A1 is equal to 3. So by putting the initial conditions to find A and B, we use initial conditions. Okay. So here A0 is equal to 0 and A1 is equal to 3. Here A0 is equal to 0 and A1 is equal to 3. Right? So you will get here A0 is equal to A into 5 raised to 0 is 5. 2 raised to 0, sorry, a raised 5 raised to 0 is 1 and 2 raised to 0 is 1. So a plus b, and here a0 is equal to 0. So you will get a plus b is equal to 0. This is first equation. Okay. Now putting r is equal to 1 because initial condition is given. So putting r is equal to 1. Putting here r is equal to 1, you will get a1 is equal to here 5a plus 2b. 5a plus 2b, but the value of a1 is given 3. We'll get here 3. So 5a plus 2b is equal to 3. Call this as equation number 2. A plus b is equal to 0 and 5a plus 2b is equal to 3. So while solving these two equations simultaneously, get here a plus b equal to 0. So if I multiply this by 5, right, comes 0 and subtract it. Here you will get 0 minus 3b is equal to 3. So which implies b is equal to minus 1. Right? And put the value of b is equal to minus 1. So you will get a is equal to 1. Yeah. Now put the value of a and b in the given equation AR. So here AR is equal to a is 1. Get 5 raised to r. B is minus 1. There is 2 raised to r. AR is equal to 5 raised to r minus 2 raised to r is the solution for the given recurrence relation. I hope you are getting it clearly how to solve the recurrence relation. Now here only the condition that here roots of the given recurrence relations are distinct, then only we can use this solution. Okay, if the roots of the given recurrence relation are real and repeated, then we will use the different solution. Okay, so for that we will use here, we'll solve this example in which we will get clear whenever the roots of the given equations are repeated, then how to find out the solution. Okay. Now the procedure is same. Use the characteristic equation first. Okay, the characteristic equation of this recurrence relation is characteristic equation of the given recurrence relation of the given recurrence relation. If we get here lambda square minus 4 lambda plus 4 is equal to 0. Lambda square minus 4 lambda plus 4 is equal to 0. That is, here you will get lambda minus 2 bracket square is equal to 0, which implies lambda minus 2 into lambda minus 2 is equal to 0, which implies lambda is equal to 2 and lambda is equal to 2. Now roots of the given recurrence relation are real and repeated. Okay, roots are repeated, therefore the solution for the given recurrence relation is roots are repeated, therefore solution for the given recurrence relation, solution for the given recurrence relation is, solution for given recurrence relation is here lambda square, solution for the given recurrence relation AR is equal to A plus BR. Now it is, here is very important, A plus BR into 2 raised to R, lambda raised to R. A plus BR into lambda raised to R, where lambda is equal to 2. Now here the initial conditions are given. A0 is equal to 1 and A1 is equal to 6. Right? The initial conditions are given. A0 is equal to 1. To find A and B, we have we put R is equal to 0. Right? That A0 is equal to A plus BR. It means here A into R is 0, so this is 0. 2 raised to 0 is 1. So only A0 is equal to A, right? So here value of A0 is given, that is 1, which implies 1 is equal to A, right? So value of A is equal to 1. Okay, now we'll put the initial condition, put R is equal to 1. So you will get A1 is equal to A plus B into 2, right? So 2A plus 2B, here A1 is equal to 6. A1 is equal to, or 2A plus 2B is equal to A1, that is 2A plus 2B is equal to 6, right? So it means A plus B is equal to 3, right? But we know that A is equal to 1, so you can put here, so B is equal to 2. So the value of B is equal to 2 and value of A is equal to 1. So the solution of this given recurrence relation is, okay, just put the value of A and B here. So you will get AR is equal to, so we get here AR is equal to 1 plus 2R into 2 raised to R plus 2R into 2 raised to R. Okay, this is the solution for the given recurrence relation. Third one, solve the following recurrence relation. Dn is equal to 2 dn minus 1 minus dn minus 2, given that d1 is equal to 1.5 and d2 is equal to 3. Okay, so we will calculate d1 here first. So d1 is equal to 1.5. So the characteristic equation is very simple. The characteristic equation is Now first write down this recurrence relation in the form. See here standard form dn minus 2 dn minus 1 plus dn minus 2 is equal to 0. So this is homogeneous recurrence relation, right? The characteristic equation is here dn is equal to characteristic equation is here we'll get lambda square 2 lambda plus 1, right? So lambda square minus 2 lambda plus 1 is equal to 0. So is it nothing but lambda minus 1 bracket square is equal to 0? So which implies lambda is equal to 1 repeated root. Okay. Therefore the solution is dn is equal to a plus bn into 1 raised to n, right? This is equation number 1. Now use the initial condition d1 is equal to, right? So to find a and b, we use initial conditions. Here d1 is equal to given 1.5, d2 is equal to 3, right? So d1 is equal to a plus b to 1, right? A plus b 1 raised to 1. So here a plus b 1 raised to 1, a plus b is equal to d1, right? So here you will get a plus b is equal to value of d1 is 1.5, right? A plus b is equal to 1.5. So a plus b is equal to 1.5. So you will get first equation or equation number 2. Now put the initial condition 2. So d2 is equal to here n is equal to 2. A plus 2 1. So a plus 2b and 1 raised to 2 is again 1. Get a plus 2b equal to 3. Call this as equation number 3. So solving equation 2 and 3 simultaneously, you will get a plus b is equal to 1.5 and there is a plus 2b equal to 3. Just subtract at minus b equal to minus 1.5 equal to 1.5. Put b is equal to 1.5 here. So you will get a is equal to 1.5 minus 1.5, that is a is equal to 0. So you will get solution dn is equal to here a0 is 1.5 into n, dn is equal to 1.5 n 1 raised to your solution for the given recurrence. Now, solve the following recurrence relation in the similar way. So solve immediately here. So the recurrence relation is dn minus 3 dn minus 1 plus 2 dn minus 2 is equal to 0 with the given condition that d1 is equal to minus 2, 2 is equal to 4. Okay. So the characteristic equation is lambda square minus 3 lambda plus 2 is equal to 0, right? So you will get lambda plus 2 to lambda minus lambda plus 1 equal to 0. So lambda is equal to minus 2 and lambda is equal to minus 1. Distribute, get the solution. Dn is equal to here into minus 2 raised to n plus b minus 1 raised to solution. If you want, you can call it, this is your equation number 1. Put the initial condition, writing the equation 1 here again, t into a into minus 1 raised to n plus b here written, n is equal to this. Now put the initial condition here, put n is equal to 1. Right? N is equal to 1 in equation 1, get equal to 1 in equation 1, get d1 is equal to here minus 2a minus b, but value of d1 is given equal to minus 2. 2a minus b is equal to minus 2. Nothing but 2a plus b is equal to 2. All this as equation number. Now put n is equal to 2 in equation 1. So we get that d2 is equal to minus 2 minus 2 square, that is plus 4, plus 4a plus b. d2 is equal to 4a plus b, right? 2 is equal to 4a plus b, and the value of d2 is given. 2 is equal to condition 4, right? Get 4a plus b equal to equation number. Now solve the equation 1 and 2 and 3 simultaneously. 2a plus b is equal to 2. 4a plus b is equal to 4. Plus 2a plus b is equal to 2. 4a plus b is equal to 4. Right? This minus 2a is equal to minus 2. A is equal to 1. So a is here 1. Now put a is equal to 1 here. 2 equal to 0. The equation n is equal to, get the solution, n is equal to a is 1. Right? Plus 2 raised to n. Your solution for the event recurrence. Hope it is clear to you how to find out the solution when the roots of the given differential equations are real and distinct, and the roots of the given differential equation are repeated. Now, then this is we have seen for homogeneous. Now we will see for the non-homogeneous recurrence. Okay, solution for the non-homogeneous recurrence relation. Now, solution using generating function. Okay. Of is a homogeneous relation is obtained by putting fn is equal to 0 in the equation. But if fn is not equal to 0, then this equation 1 is called as equation number 1, known as non-homogeneous recurrence relation. Solution of equation number 1 is called as particular solution. So there is no general procedure for determining the particular solution. It depends upon nature of f of n. Okay. So the homogeneous solution of the linear equation, linear recurrence relation, is denoted by ANH, and the particular solution is denoted by A at P. And the addition of these two solutions are called the total solution of a given non-homogeneous linear recurrence relation with constant coefficient. Thus, the total solution N is given by N is equal to N at H plus N at P. Right? Now, there are 5 distinct conditions to find out the particular solution depending upon the nature of Fn. Now we know that homogeneous. How to find out the non-homogeneous recurrence solution for the non-homogeneous recurrence relation? First convert it into homogeneous and find out N at H. Okay, and then here by depending upon the nature of Fn, we will find out N at P. An addition of N at H and N at P will give the total solution for the given non-homogeneous recurrence relation. Okay, so these are the 5 cases. If Fn is a constant, then n at p is equal to p. If Fn is equal to c0 plus c1n, that is linear function, then n at p is equal to p0 plus p1n. Directly we can write. If Fn is a linear combination of this linear equation kth degree polynomial, then n at p is p0 plus p1 at n plus p2n square plus and so on pk into n raised to k. If Fn is equal to c into b raised to n, provided b is not the characteristic root, then n at p is equal to p into b raised to n. And if Fn is equal to c into b raised to n, where b is the characteristic roots of the equation with multiplicity m minus 1, then n at p is equal to p of n raised to m minus 1 into b raised to n, depending upon the nature of Fn, the particular solution for the given recurrence relation. Okay. Now first of all, see the solve the difference equation with the given boundary condition. Okay. So we will solve the given recurrence relation, the boundary conditions. Now first one. So first step is, first of all, convert it into homogeneous recurrence relation. Okay. The corresponding homogeneous recurrence relation for this is corresponding homogeneous recurrence relation recurrence relation is AR minus 5 AR minus 1 plus 6 AR minus 2 is equal to 0. Now follow the same process of this homogeneous recurrence relation as we have seen earlier. So here the characteristic root is the characteristic roots of this equation. Characteristic equation of this recurrence relation. Recurrence lambda square minus 5 lambda plus 6 is equal to 0. Right? Here lambda minus 3 into lambda minus 2 equal to 0. Get lambda is equal to 3 and lambda is equal to 2. Okay. Roots are real and distinct, so the solution is ARH, homogeneous solution, A into 3 raised to R plus B into 2 raised to the homogeneous solution. Okay. Now to find the particular solution, we consider the term f of R, right hand side of the given equation. The given equation f of R is equal to 2 raised to R plus R. Okay? Here f of R is equal to 2 raised to R plus R. Now we will find this. Now since here 2 is the root, right? So 2 is the root of the characteristic equation. 2 is the root. Very important. 2 is the root. First of all, check the root. Here 2. So 2 is the root of the characteristic equation. Okay. So that we have particular solution. Is, and it is a linear combination of two roots. You see here, it is a linear combination of two roots. Here, f of r is equal to here 2 raised to r plus r. Here f of r is equal to 2 raised to r plus r. So linear combination. So both the cases here we are using p of r raised to 1 into 2 raised to r, because 2 is the root of the characteristic equation. So here we see we will apply the case 5. 2 is the root of the characteristic equation with multiplicity here 2. So 2 minus 1 is 1. So p of n into 2 minus 1 into 2 raised to n. Right? That's it. We have written p1 of r raised to m minus 1 into 2 raised to r. Right? Plus, for this, p2 plus p3r for constant linear combination. Okay? So two terms are there. So p2 plus p3. Now substituting in the given equation, we get, substituting this in the given equation, we get, can write down this. What is your given equation? Given equation is AR minus 5 AR minus 1 plus 6 AR minus 2 is equal to 2 raised to R plus R. Right? So put, there is 2 raised to here, 1 into, I'm putting directly here, substituting P1 R raised to 1 into 2 raised to R plus P2 plus P3R minus 5 into 1 into R minus 1 to 2 raised to R minus 1 plus P2 plus P3R minus 1 plus 6 into bracket P1 into R minus 2 into 2 raised to R minus 2 plus P2 plus P3 into R minus 2 is equal to 2 raised to R plus R. Right? So therefore, 2 raised to R to P1R minus 5 by 2 P1 to R minus 1 plus 3 by 2 into P1R minus 2 plus 2P2 plus 2P3R minus 7P3 equal to 2 raised to R plus R. Now just compare the coefficient. So here AR is equal to, as it is, here this is your AR. So AR is equal to this, minus 5 into AR minus 1 plus 6 into this. So take 2 raised to R common from all this and take 2 raised to R minus 1 common from all this. So you will get this, which is equal to 2 raised to R plus R. Now comparing the coefficients here, which implies 2 raised to R. After simplifying this, you will get minus 1 by 2 P1 plus 2P3R plus 2P2 minus 7P3 is equal to 2 raised to R plus R. 2 raised to R into bracket minus 1 by 2 P1 plus 2 P3R plus 2 P2 minus 7 P3 is equal to 2 raised to R plus R. Now we will comparing the coefficient. On comparing coefficients of R, and we get not only R, raised to R and R both. Okay. Next is minus P1 by 2 is equal to 1, 2P3 is equal to 1, 2P2 minus 7P3 is equal to 0. Right? So ultimately here P1 is equal to minus 2, P2 is equal to 1 by 2, P2 is equal to 7 by 4. Okay? P3 is equal to 1 by 2, put here, so you will get P2 is equal to 7 by 4. So which implies, therefore, A3 AR at P is equal to minus 2R into raised to 1 by 2, 7 by 4R. Right? Therefore, total solution is, AR is equal to AR at H plus AR at P. So we know that AR at H So AR is equal to A into 3 raised to R plus B into 2 raised to R minus 2R into 2 raised to R plus 1 by 2 plus 7 by 4 R. Okay, final. Now using the bound, this is your solution. Now we'll use the boundary conditions and find out A and B. Okay, so using boundary conditions or initial conditions, boundary conditions, we get A0 is equal to A plus B plus 1 by 2. That is A plus B plus 1 by 2. Here A0 is given 1. Implies A plus B implies A plus B is equal to 1 minus 1 by 2. That is 1 by 2. Right? R is equal to 1. R is equal to 1. So A1 is equal to A plus 2B minus 4 plus 1 by 2 plus 7 by R. Okay. After this, you get 1 is equal to A plus 2 A plus 2 is equal to, you will get minus 4 the minus 16 2 plus 7 on 4 minus 16 plus 9 plus 7 minus 9 by 4 minus 9 plus 2 minus 7 by 4. Here get minus minus 16 plus 2 plus 7 and plus 2 9 minus 16 plus 9 minus 16 plus 9 minus 7 by 4. Yeah, 7 by 4 plus 2b is equal to plus 2 equal to 11 by 4. 1 plus 7 by 4, that is 11 by 4. So 3a plus 2 equal to 11 by 4. This called this as equation 1. As equation, solving equation 1 and 2 simultaneously. Equation 1 and 2 simultaneously. Let a is equal to 7 by 4 and b is equal to minus. Just put in that solution AR is equal to 7 by 4 into 3 raised to 5 by 4 raised to R into 2 raised to R plus 1 by 2 plus 7 by 4 R. Right? Here AR is equal to 7 by 4 into 3 raised to R plus R plus 2 raised to R into minus 5 by 4 minus 2R plus 1 by 2 is your given solution for the given non-homogeneous recurrence relation. The process is much lengthy, but first we get to solve this non-homogeneous. Now, all this recurrence relation. Now here is equal to 2 raised to n, so obviously it is a non-homogeneous recurrence relation. The initial condition a0 is equal to 0, a1 0, and a2 is equal to 2. Now, first job is converted into homogeneous. The corresponding homogeneous recurrence relation is the corresponding homogeneous recurrence relation is an plus 6n minus 1 plus 12n minus 2 plus 8n minus is equal to 0. Characteristic equation, that is equation is the let lambda constant lambda square lambda cube. So lambda cube plus 6 lambda square plus 12 lambda plus 8 equal to 0. Is it nothing but you can find out by using the synthetic division also, but here I am taking here lambda plus 2 bracket cube equal to 0. So you will get lambda is equal to minus 2 minus 2 minus 2 dead row, right? Hence homogeneous solution is hence homogeneous solution is a net h equal to a1n square plus a2n plus a3 to minus 2 raised to the particular solution. The particular solution will be of the form into 2 raised to n, substituting the given in the given recurrence relation. The particular solution will be of the form p 2 raised to n, because 2 is not minus 2 is the root, 2 is not the root, so directly you can write p into 2 raised to n, right? P into 2 raised to n. Here, so because here 2 raised to n, f of n is equal to 2 raised to n, but 2 is not the root, so we can apply the case here. We'll apply the case 4. P is not the characteristic root. Here minus 2 is the root, 2 is not the root, so directly you can write a net p is equal to 2 in p into 2 raised to n. Substituting in the given recurrence relation, the given recurrence relation, we get p into 2 raised to n is 12 minus 8 into raised to n plus 3 equal to 2 raised to n, implies 2 raised to n into p bracket 1 plus 6 by 2 plus 12 by 4 plus 8 by 8 equal to 2 raised to n. Right? So taking 2 raised to n minus 1, it means 2 raised to n into 2 raised to minus 1, but 2 raised to minus 1, it means 1 upon 2. Right? This is your, so 2, which implies 2 raised to n in p into bracket get, now 2 raised to n cancel out from the side. P into bracket 1 plus 3 plus 3 plus 1 equal to 1, right? Plus 3, 6 plus 2, 8, 8p equal to 1, equal to 1 by 8, okay? Equal to 1 by 8. Net p, let a net p is equal to 1 by 8 into 2 raised to nothing minus 3, because 2, 8 it means you can write 2 raised to 3, 3 to 2 raised to n, so 2 minus 3. A net p is equal to 2 raised to n minus 3. The total solution is n is equal to a net h plus a net. Okay. Get here n is equal to a net h is given a1 n square plus a2 n plus a3. Bracket minus 2 raised to plus 2 raised to n minus 8. Now using the initial conditions, we will find a1, a2, a3. Initial conditions, find 1, 2, a0 is equal to a0 is equal to 0, given a1 is equal to 0 and a2 is equal to 2. These are the initial conditions. Now put n is equal to 0, so a3 only. a3 is equal a3 plus 1 by 8 is equal to a3 plus 1 by 8. Let here write down like this. Okay. Equal to by implies a3 is equal to minus 1 by 8. Let a3 is equal to minus 1 by 8. Put that. So 0 is equal to, put a1 equal to 0. 1 0 equal to a1 plus 8 plus a3 to minus 2 raised to 1 plus 2 raised to 1 minus 3. a1 plus a2 plus a3 equal to 1 by 8. Call this as equation number 2. Okay. Equal to minus 1 by 8, equation number 1. So 2 is equal to 1 4 plus a2 plus a2 minus 2 square plus 2 raised to 2 minus 3. Right? Equal to 2 is equal to 4a1 plus 2a2 plus a3 into 4, 1 by 2. Right? 3 by 2 is equal to 2 minus 1 by 2. So 3 by 2 equal to 4 into bracket 4a1 plus 2 plus 8 by 8 equal to 4a1 plus 2 plus 2a2 plus 8. Number 3. Solving equation 1, 2, 3 and simultaneously. 1 and 3 simultaneously. Get a1 is equal to 0, a2 is equal to 1 by 4, a3 is equal to minus 8. Right? Therefore, an is equal to here 1 by 4 minus 1 by 8 into plus 2 minus 8. equal to 1 by 4n minus 1 by 8 to minus 2 raised to n plus 2 to n minus 3. Your solution for the given recurrence relation. Okay. Solve the given recurrence relation. One more solution we will find out. Okay. Solve the recurrence relation non-homogeneous. Solve the recurrence relation. Solve the recurrence relation. An is equal to 2an minus 1 plus 3an minus 2 plus 5 raised to n, where n is greater than or equal to 2. When that the initial conditions are a0 is equal to minus 2 and a1 is equal to 1. Okay. Therefore, the recurrence relation will be minus 1 minus 3n minus is equal to 5 raised to n. Actual recurrence relation. Therefore, characteristic equation is constant lambda square minus lambda plus 3 is equal to 0. Get lambda plus 1 into lambda minus 2 lambda 3. Lambda is equal to minus 1. Lambda is equal to further homogeneous solution a at h equal to a into 3 raised to n plus b minus 1. So for the particular solution, Fn is particular solution. Fn is given. Fn is equal to 5 raised to. Okay. Now, therefore, the particular solution is at p equal to p into 5 raised to n, because 5 is not the root of the given characteristic. Substituting this in given recurrence relation, this given recurrence relation have here get here p into 5 raised to n minus 2 into 5 raised to n minus 3p into 5 raised to n minus 2 is equal to 5 raised to n. Implies 5 raised to n into bracket 5 raised to n into bracket 1 minus 2 by 5 minus 3 upon 5 square is equal to 5 raised to n. Implies into 12 by 25 equal to 1. Size equal to 25 square. Therefore, the particular solution, therefore, partition is n at p equal to 25 by 12 into 5 raised to the complete solution. The complete solution is equal to at h a into raised to 20 fell into using the initial condition. Find value of a. Initial condition. Find of a and b. For the initial condition equal to a1 is equal to 1. Get equal to a plus b plus 25 by 12. Right? A plus b is equal to minus 49 by 12. So 1 is equal to a by putting a1 is equal to 1. A minus plus 12 5 by 12 into 5. 4 minus b equal to 1 minus 120 is equal to minus 113 8 a minus b is equal to by 12 by 12. For solving equation equation 2, adding this get cancel out equal to minus by 12. A is equal to minus 27 by 8 equal to minus by total solution is a minus 7 by 8 plus 2 17 by 24 and rest to 20 12 the solution the V1. I hope you are getting it clear. Total recurrence relation. I explain all the conditions here when the given in the homogeneous non-homogeneous if root of the given characteristic equation, then how to find out the particular solution, and if not given root is not the root of the given characteristic equation, then how to find out the particular solution. Okay, so everything is clear to you, I hope. We have covered homogeneous recurrence relation. In that roots are distinct and roots are repeated, and non-homogeneous recurrence relation in which roots are repeated and distinct also, and to three conditions whenever it is in linear combinations. So I hope I cover up here 1, 2, 3 conditions here. When the constant is there, I will not cover it. That will also part you can easily cover up here. The constant part also. If you want, I will cover one more example so that you will hear how to find out the solution for the given non-homogeneous recurrence relation. For example, so solve the following recurrence relation. Here. Following recurrence relation. The following recurrence relation. Here AR minus 3 AR minus 1 equal to 2, where R is greater than or equal to 1 and A0 is equal to 1. Okay, the condition is very simple. The characteristic equation first, the homogeneous recurrence relation. AR minus 3 AR minus 1 is equal to 0. The characteristic equation is characteristic equation here lambda minus 3 equal to 0, so lambda is equal to 3. That's it. Okay. R at h equal to R at h equal to A into 3R. Out the AR at P, the particular solution of the type P only. Particular solution was only constant of the type P only. Is constant. Okay. Let AR equal to P. Now put this in the given substituting the value of AR. Substitute the value of AR and AR minus 1. The given recurrence relation. Recurrence relation. That is P minus 3P is equal to 2 minus 2P equal to 2 equal to minus, right? Equal to minus 1. So you will get AR is equal to, I'm writing here only, AR is equal to A into 3 raised to R minus 1, right? So using initial conditions, you will get A0 is equal to 1. So 1 is equal to A minus 1. So A is equal to 2. Okay? Your final answer AR is equal to here 2 into 3 raised to R minus. I hope you are clear here. AR is equal to here solution AR at H and AR at P. But P is equal to minus 1. AR at H is 2 into 3 raised to R minus. Final solution and the constant is there. So I hope you are clear here. I covered up most of the cases. See, n is equal to p constant. Just now we have seen fn is equal to c0 plus cn 2 raised to r plus r in that form. And the polynomial similarly we will get fn is equal to c into b raised to n, where b is not the characteristic root, that is 5 raised to n का example हमने देखा है यहाँ पे. fn is equal to c into b raised to n, that is 2, the same characteristic root of the equation. So I covered all the cases here for to solve the non-homogeneous recurrence relation and how to find out the particular integral by using these functions. Okay? I hope you are getting it clear very clearly. If you are liking my videos, to like, share and subscribe. And one more thing I'm going to tell you, I will be here from Monday in the next channel, another channel, that is Unacademy's semester exam. Okay, so I will meet there for the Unacademy semester exam. So keep watching. If you are liking my videos, please do like, share and subscribe. Thank you so much. I will be here tomorrow at the same time 11:15 with a new topic, that is group theory. Cover up the group theory from next lecture.